Hello everyone, I am Dr. Neelakanteshwar Rao from EEE Department of VNR JYOTHI Institute of Engineering and Technology. I am dealing a set of lecture series in Power Systems 1 course. In last class, we have seen how to calculate inductance of a transmission line due to flux linkages which are external to an isolated conductor. In this class, let us see some calculation of inductance for a single phase transmission line. So before that, let us calculate the flux linkages and current of an isolated conductor. So, calculation of flux linkages and inductance of an isolated conductor due to flux up to an external point. So for that, let us consider an isolated conductor. So let this be some isolated conductor. Now let us calculate first the flux linkages of this isolated conductor. So when we say isolated conductor, we mean that we do not have any other conductors in vicinity of it which disturbs the flux linkage of this conductor. So that is meant by isolated conductor. So we have considered an isolated conductor. And now when we say flux linkages or flux around this conductor, that is not limited to a particular point, but it has no bounds. It moves to infinite distance. So for that reason, we calculate flux linkage of this conductor till some point. So let us say that we want to calculate flux linkages to some point P, which is at a distance d meters from the center of the conductor. Let this distance be some d meters, and let r be the radius of the conductor. And let I be the current flowing through it. Now when I say flux linkages of the conductor, which we represent by lambda, this could be due to the flux which is produced inside the conductor. Then we can take it as lambda internal plus the flux which surrounds the conductor surface, which can call it as lambda external. Lambda internal is a constant which we have seen in one of the last sessions. So let us first now calculate lambda external from the center of the conductor till point P. So in last lecture we have seen if we want to calculate the flux linkage between 2 points, is given by, if the 2 points are 1 and 2, we may write lambda 1 2 is equal to 2 into 10 power minus 7 into the current which is flowing in the conductor multiplied by log of d2, which is the distance from the center of the conductor to the farthest point, to d1, which is the distance from the center of the conductor to the nearest point. So and so Weber turns per meter. Now for our case, lambda external can be similarly expressed as 2 into 10 power minus 7 into the current which is flowing through the conductor, which is I, into log of, now d2 was the distance from the center of the conductor to the farthest point. So here we have considered only a single point P. So d2 can be replaced by capital D, and the nearest point from the center of the conductor is the surface of the conductor, which is at a distance of r meters from the center of it. Why? Because r we have considered to be the radius of the conductor. So d1 can be replaced by small r. So and so Weber turns per meter. Now if I want total flux linkages lambda, we have seen above that this is equal to the internal flux linkages plus the external flux linkages. And in one of the last sessions we have seen the internal flux linkages is given by I by 2 into 10 power minus 7. And from the above expression we can write the external flux linkages as 2I into 10 power minus 7 log d by r. So if I take 2I into 10 power minus 7 common in them, then in first term we get 1 by 4, and in the second term we get log of d by r. Now this can be further reduced, like this implies lambda is equal to 2I into 10 power minus 7. Now I can write 1 by 4 as 1 by 4 into log E base E plus log of d by r to base E. So this again I can write it as 2I into 10 power minus 7 into log e power 1 by 4 base E plus log d by r base E. It implies lambda is equal to 2I into 10 power minus 7 into, now the above expression is in the form of log a plus log b, which will be equal to log ab. Then this can be written as log d e 1 by 4 by r. So here if we want we can take the base as E, or even if it is not mentioned, by default the base would be E. So this I can also write it as 2I into 10 power minus 7 into log of d by, I'll get e power 1 by 4 to denominator inside the parenthesis of logarithm, then that becomes e power minus 1 by 4. This I will write it as 2i into 10 power minus 7 into log of d by r dash, where r dash is given by r into e power minus 1 by 4, and this comes out to be 0.7788 into r. So this would be the expression for flux linkages of an isolated conductor by considering flux linkages till some external point which is a distance d. So from this, if I want to calculate inductance of an isolated conductor, then that would be some L is equal to ratio of flux linkages to current, which is equal to, from above expression, 2 into 10 power minus 7 log d by r dash, and the units of it will be Henry per meter. Right. So this is about calculation of inductance of an isolated conductor. Now let us move on to exact topic of today, which is calculation of inductance for a single phase transmission line. So for that, let us consider two conductors, something like this. So here, now the next topic would be calculation of inductance for a single phase transmission line. Now let those two conductors be as one, what I have shown here. Let I1 be the current which flows in conductor 1, whose radius is R1. So this radius is R1. And let I2 be the current which flows in the second conductor, and let the second conductor radius be R2. Right. Now the conductor 1, which is carrying current I1, forms the forward path or creates a forward path for the flow of current I1, and the conductor 2, which is carrying I2, will become the return path for the flow of current through it. So from this we may say I1 plus I2 will be equal to 0, or I2 is equal to minus I1. Right. Now, first let us consider the flux which is produced by conductor 1 alone. And we know that when we say the flux which is produced by a conductor, it will be in the form of concentric circles around it. So here I have taken that case where I'll be considering the flux produced by conductor 1 alone. So here I have drawn that. So here the dashed line which you can see represents the flux lines which is produced by conductor 1 alone. So here you will have a better view. Right. So let the distance between the first conductor center and the second conductor center be some capital D. That is, the distance of separation between the conductors be some capital D. Since conductor 2 is having radius R2, from center of conductor 1 to the surface of conductor 2 will be now D minus R2. Similarly, from center of conductor 1 to the outer surface of conductor 2, the distance will be D plus R2. This will be D plus R2. Right. So in conductor 1, I1 is the current flowing, and in conductor 2, I2 is the current flowing. And here we are considering only the flux which is produced by current which is flowing in conductor 1. So let us give some numbers to these flux lines. Let the first flux line be some 1. Let the second flux line be 2. And third flux line be 3. And fourth be 4. Similarly, fifth is 5. And sixth is 6. So here you can see the flux lines 1, 2 and 3 are completely linking the current which is flowing in conductor 1. And if you see flux line 5, it is linking the currents which are flowing in both the conductors. Why? Because this flux line is surrounding both the conductors. So it is linking both the currents I1 and I2. And we have just now seen that the sum of these two currents is equal to 0. So the net current linked by the flux line 5 is 0. Similarly, if you see flux line 6, it surrounds both the conductors. So it is linking the net current, which is I1 plus I2, and it is equal to 0. So the flux linked by the flux line 6 is also 0. So here these are these observations. So one more observation what you can make is, if you see flux line 4, it is linking partial current which is flowing in conductor 2. So here what you can say is, from this what you can say is, you can say that the flux from the center of the conductor 1 till the inner surface of conductor 2 links the entire current which flows in conductor 1, and the flux from that is above or beyond the external surface of conductor 2 links a net 0 current, and the remaining flux lines between the inner surface of conductor 2 and the outer surface of conductor 2 links a current whose magnitude goes on decreasing, and when it comes to the outer end, the net current linked would be 0. So these would be the observations from this single phase transmission line. So based upon these observations, we can make an assumption that the flux from the center of conductor 1 till center of conductor 2 links the entire flux, links the entire current which is flowing in conductor 1. I repeat again, the flux from surface of conductor 1 to the inner surface of conductor 2 and the center of conductor 2 links the entire current I1, and the flux from center of conductor 2 till the external surface of conductor 2 links a net 0 current. So let us put that in words. The flux from center of conductor 1 to center of conductor 2 links the entire current flowing in conductor 1. And the flux from center of conductor 2 to its outer surface which is at distance d plus r2 from center of conductor 1 links a net 0 current. So this is the assumption. This assumption is valid when d, the distance of separation between the conductors, is quite greater than the radius of either conductors. And this is quite acceptable. Why? Because in overhead transmission lines, the radius of the conductors are quite less compared to distance of separation between them. Now, with this assumption, what we have stated, the flux linkages of conductor 1, if I call it as lambda 1, will be equal to 2 into 10 power minus 7 into the current which is flowing in conductor 1 multiplied by log of the distance of separation between the conductors is d divided by r1 dash. And if I want inductance of conductor 1 that I can call it as L1, which will be equal to lambda 1 by I1, which will be equal to 2 into 10 power minus 7 into log of d by R1 dash, so and so Henry per meter, and flux linkage will have a unit Weber turns per meter. Now, similarly, inductance of conductor 2, if I call it as L2, that would be equal to 2 into 10 power minus 7 into log of d by R2 dash, so and so Henry per meter. Now, if I want total inductance of this single phase transmission line, I can call it as capital L, which is sum of L1 and L2, which comes out to be 2 into 10 power minus 7 is common in both the terms. That would be log of d by R1 dash plus log of d by R2 dash. Then it implies L is equal to 2 into 10 power minus 7 log of d square by R1 dash R2 dash. This can again be written as 2 into 10 power minus 7 log of d by under root R1 dash R2 dash whole square. It implies L is equal to 4 into 10 power minus 7 log of d by square root of R1 dash R2 dash, so and so Henries per meter. Now, if we consider the radius of both the conductors to be same, that is, if R1 is equal to R2 is equal to R, then this L will be equal to 4 into 10 power minus 7 ln d by R dash, so and so Henries per meter. So this will be the total inductance of a single phase transmission line. Thank you for today.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.